Ngalakin kadijan yung boja.
Okay, good afternoon, everyone. So let's start our practical class for this week. Before we start the class, a good news for you. Professor Tyrone is coming back. So highly possible on this Wednesday, he will be back in this lecture on Wednesday. But if he's not able to cover the class for this week, maybe I will be here again on Wednesday. But from next week, what do we mean? So highly possible, almost 99%. He will be back in next week for both of the practical class and the lecture. For the lecture on this Wednesday, so far I have not seen him yet, so I can't comment on that. So maybe Tyrone, maybe me for this week in lecture, okay? And for our practical class today, we are going to focus on the, sorry to say, we're still in the tutorial 2, the transmission lines, this chapter. And in the lecture last week, we have already discussed 3 things. One is a short transmission line model. The other is a medium-sized transmission line model. So these 2 things should be fine. On the top of these 2, we also discussed the ABCD, the 2-port network model. Okay. So in our tutorial question discussion today, we are going to focus on these 3 topics. And in the tutorial 2, we have in total 1, 2, 3, 4 questions, I think, only 4 questions. The question number 4 is about long transmission cable. We have not learned that thing yet, so we are not going to discuss the question number 4 in our tutorial today. highly possible I will leave that to Tyrone for next week's practical class. Okay, and in other words, in our class today, our questions will be just the first three in the tutorial 2. And out of these 3 questions, they are pretty simple. And only the question number 3 is a little bit tricky. So we are going to plot our phasor diagram for this given medium-sized transmission line model. So this may be a little bit challenging for you. But the first 2 questions should be pretty straightforward. Okay, so let's start from the first question. In the question number 1, we got 25 kilometers long. Once we read this condition, we know this is a short transmission distance because it's smaller than 80 kilometers. So by default, we should use a short transmission line model for this question. Okay, so 25 kilometers, 34.5 kilovolts, 60 hertz, 3-phase line has a positive sequence. So in other words, ABC sequence. Series impedance Z equal to 0.19 plus J 0.34 ohms per kilometer. This is lower Z given in the condition is actually the unit impedance of the transmission line. Shortly, when we work out the total impedance, we have to use that 25 kilometers multiple this unit size impedance to get the total impedance. Okay, we talk about later anyway. The load at the receiving end absorbs 10 mic VA. So what is this power? Apparent. Do you have the phase angle information? Yes, because the complete power is a vector having magnitude and angle. But this question is talking about only the magnitude. So this is apparent power. So the apparent power received by the users is 10 MVA. The voltage is 33 kilovolts. So assuming a short transmission line, so please calculate A, the A, B, C, D parameters. I think the question A is very simple. But before talking about solutions, let's just quickly review what is ABCD model. The ABCD model is used for the 2-port network systems. And we are modeling all our transmission cables to be the 2-port networks. So in other words, regarding question number 1 here, so here we are going to create a black box we mentioned last week. This is our transmission line cable. And on the left-hand side, we assume that is the sending end. So we have the 2 input ports. So give us the sending end current and the sending end voltage source, the voltage. And on the other side, which is the user side or the receiving end, we have IR. IR is the receiving side current, and also, we have the receiving side voltage. Okay, inside of this black box, we are going to use ABCD model to model it. The mathematical expression for this ABCD model is, so we are using the matrix form, okay, the compact form of that. So VS, IS, the 2 unknowns on the sending end is equal to our ABCD model. So we are using the 4 items in this matrix to denote the ABCD model. And the multiple, we are IR. So this is just ABCD model we used. But regarding different transmission line models, the A value, B value, C value, D value will be different. But I think for this question, because we are supposed to use short transmission line model, so these A, B, C, D items should be very simple. So if you got short line transmission model, so the ABCD model for short transmission cable should be like very simple. Can you recall what should be the elements? First of all, along the diagonal direction, the 2 elements should be same. For short transmission cable, which is 1 and 1. For the off-diagonal elements, Z and 0. Just that. Very simple. Much easier than the medium and the long-size transmission models. So if you have already known what ABCD model we should use for this question, and we just need to focus on how to solve the unknown thing, the Z. This Z is total impedance of the transmission line. And we have already known, so for unit size transmission line, its impedance is, so I can't remember the values, but anyway, I copy this from hard copy, 0.19 plus J by 0.34 ohms, yes, per kilometer. And we also know the transmission distance D is 25 kilometers. So based on these two values, the total transmission line impedance, the total one for the whole 25 kilometer line, is equal to the Z multiple the transmission distance. Okay, guys, I didn't do the calculation at all, so I copied this one from our solution. Okay, so it should be very simple for you because it's just a 25, this real number, multiple that's unit size impedance. The result should be, so in phase form, 9.737 with 60.8 degrees ohms. Get that? So I copied this number from the solution, but it should be easy for you. Okay. This Z should be used as the B item in this matrix of the ABCD model. So that should be easy thing. Okay. Now this is just all the conditions we have, and by solving this question, we have already got the A, B, C, and D. These four parameters in the ABCD model. So the part A of the question is solved. So this should be easiest part. Part B. Okay, let's go back to our question and have a look at part B. Part B is asking, so the sending end voltage. So the question is asking us to calculate the sending end voltage for a load power factor of 0.9 lagging. So actually, based on the ABCD model we developed from the part A, okay, we are talking about this whole thing, right? Oops, this whole thing here. The question B is asking us to determine what is the value of the sending end voltage. Sending end voltage is given here, Vs. So you want to solve the Vs based on the ABCD model. The Vs should be equal to AB item in this matrix, the first row of this ABCD matrix, multiple the VRIR column, and add up the product of the two things together. So in other words, for part B, our idea is to solve the Vs by using A element, multiple the first element in the vector. So A by VR plus B by IR. A and B, these two parameters are not are known now. So we know that A is 1 and B is the actual Z, which has been solved in part A. So A and B is no problem anymore. VR. Okay, everyone, question. What value we should put here for VR? You may just go back to our question to check. First of all, VR, this R means the receiving end voltage. Can we find this value from the condition? At the receiving end, the voltage is 33 kilovolts, right? But in the ABCD model, when you calculate, the VR and the IR should be vectors rather than the magnitude. Then what is the angle for the VR vector? Why 0? Very good one. So last week, in all the class example, lecture examples we mentioned, VR, the receiving end voltage, is always used as a reference. For this reference, the angle, by default, we assume is always 0. So in other words, for this case, even though we have only the single magnitude for the VR, so this vector VR, okay, I just slow down. VR, this magnitude is 33 kilovolts. But from this one, because VR is used as reference, so the vector VR with a bar on top of it is actually 33 kilovolts. So actually, I put the kilo thing at the end. It's 33 kilovolts with 0 degrees. This is a VR. And this vector will be used to be our VR given in this equation. VR solved. So next question. What's IR? Because on the right-hand side, we have 4 parameters. A, VR, B, IR. A, B are known. VR is solved. So only question left is IR. So everyone, please be reminded, this IR cannot be magnitude only. This IR must be a vector having both of the magnitude and the angle. Is that okay, everyone? But how to determine IR? Of course, we are focusing on the receiving end. And at the receiving side, in addition to the voltage, we know one more thing. 10 MVA. We mentioned this 10 MVA is what? Is the apparent power. So everyone, you help me please. What is the formula calculating apparent power? Before you answer me, I want to remind you, apparent power is not a vector, it's a value. Okay? So how to calculate apparent power? So here, I'm not using S with bar. S with bar is the complex power. This is a vector. So this is not our focus. Now our focus is just S, which is apparent power. For a three-phase power system, the apparent power equal to, you have two formulas. First one, number 3. Number 3 means you have 3 phases, multiple, V what? V by I, of course. V what? Line-to-line voltage or phase voltage? Okay, the other formula, I gave you the other formula, is square root 3 by V something, I something. So now, for the top formula here, what voltage we should use here? Line-to-line voltage or phase voltage? Right, phase voltage. So I think here I just write down V5 to make the things shorter. It means phase voltage. In the solution, I think we are using VAN. A means phase A, N means neutral. So A2 neutral means the phase voltage, same thing. Okay, but here I'm using V5. Next formula, we should use the line-to-line voltage. For the current, do we need to distinguish is that phase current or the line-to-line current? Doesn't matter, because we are assuming the connection pattern is Y pattern. So phase current and line current are the same. So just that. For this question, what we have is we want to determine the current. We want to determine current between the formula 1 and formula 2. Which one is more convenient for us? Okay, this apparent power is not a big problem. We know the value is something like the 10 MVA. And if you want to determine the current, you want to determine which formula should be to be used. So your key factor is the voltage. Do you know the phase voltage? Or do you know the line-to-line voltage? Line-to-line voltage, right? How much the line-to-line voltage is? That's right. Very nice. Okay, everyone. So even though in the condition of question, we just give you a number, so 33 kilovolts. This 33, you need to understand, is the voltage across the transmission lines. So actually in the lectures we have mentioned, from the viewpoint of the transmission lines, we don't care the connection pattern of the users. So we just assume the line-to-line voltage is given like this. So this 33 kilovolts is a line-to-line voltage. So if you have already known the line-to-line voltage, that means this term is known. So line-to-line voltage is okay. Square root of 3 is constant. This S apparent power is 10 by 10 power to 6 VA. Of course, you can determine what's I. So I equal to, again, I don't do calculation, I just give formula, okay? It's S over square root of 3 VLL. After we finish this calculation, so we will got one current I value, right? So again, everyone, sorry for so many questions. In this current I, we derived from this step a value of the current or a vector of current. Value, just value, because apparent power doesn't have an angle. This VLL is magnitude, is also a value. The ratio of these two things is just a value. In other words, it's the magnitude of this current vector. So I just copy if you don't mind. It's 0.175. How much? I think kiloamps. Yes, that's reasonable. Okay. But as I mentioned, this is not good enough. If you want to use ABCD model to solve the VS, this current must be a vector. But so far, we just got one magnitude of current. How can we determine the angle of it? What's the angle of the IR, receiving side current? Do we have any information available to determine that? That's right. So here, at the load side, in other words, at the user side or receiving side, the load has a power factor 0.9, lagging. Lagging means the current lags voltage. Okay, so anyway, I just write this down. Because at the load side, the power factor is 0.9 lagging. Lagging means current IR lags the VR. That means if we are using the VR to be the reference, so the VR is always pointing to the positive direction of the reaxis. So we call this as VR. The angle is 0 degrees. But this IR is lagging the voltage. So that means the angle of the IR must be smaller than the angle of the VR. If the VR angle is 0, so the IR angle must be pointing to the negative direction because it's lagging. Now the question is, how much is this? Based on this given power factor 0.9, I think this angle should be pretty simple. This angle is the theta IR equal to arc cosine 0.9. Based on this calculation, your result should give you a positive angle, which is 25.84 degrees. But guys, please be reminded, because you have already known this is a lagging case, so when you calculate the angle of the current, you must put the sign in front of it, so that to indicate the correct angle of the current. So this is negative 25.84 degrees. So based on this thing, we have already known the magnitude and the angle for this receiving side current. So by combining this magnitude and angle information together, we can write our IR receiving side current vector is equal to, so how much? 0.175 kiloamps with a negative 25.84 degrees, so Ka. So this is IR. After this up, the remaining things are pretty simple, right? So IR is known. So substitute the IR back into our ABCD model. So IR is known. This, again, is a vector having both of magnitude and angle. VR, by default, the angle is 0, but VR is also vector. A and B, these two parameters are known. So put everything into the right-hand side of the equation, then you can solve the VS. The result of the VS is also a vector. Then the part B is solved. Is that okay, everyone? All good? Very last question regarding part B. Yes, after using all these values, we can solve the VS. This VS is a sending end voltage. Is this VS a phase voltage at the sending end or line-to-line voltage at the sending end? So if you want to determine if this quantity is a line-to-line voltage or phase voltage, you must check on the right-hand side. So regarding this VR, are you using the phase voltage of the receiving side or the line-to-line voltage of the receiving side? But I remember this VR we use here is the phase voltage. I can't remember. We didn't mention it? Oh, yeah, here. Yeah. So here, two stories. For my end, I'd like to use the line-to-line VR because we got 33 kilovolts, right? This 33 kilovolts is the VR at the receiving side as a line-to-line voltage. If you are using the line-to-line VR on the right-hand side of the ABCD model, so after you figure out the whole thing, the VS on the left-hand side should be the line-to-line sending end voltage as well. But the solution is telling the different story. See here, in the part B solution, at the very beginning, we are using the 33 with 0 degrees divided by square root of 3. What we are doing here, we are converting the receiving end line-to-line voltage to phase voltage. And then this VR number is used in the ABCD model. If you are using this phase voltage of the receiving end as a VR, so the derived VS will be the phase voltage of the sending end. Make sense? Then you can see after we finish this calculation, we are deriving the VS. This VS in this solution is actually the phase voltage at the receiving side, at the sending end. So everyone make sense? Is that okay? And the very last step, we are converting that sending end phase voltage to the line-to-line voltage. Do you think this answer is right, everyone? Go ahead, what's the question?
So
line to line always. Okay, unless the questions state otherwise. Okay, because actually, as mentioned, we have different connection patterns between the voltage generators and users. So from the viewpoint of transmission lines, we don't really worry about this stuff. We always focus on the line to line voltages. Yes, please. Yes. It's just zero. It's just zero. S is the Siemens. It's Siemens, yes. Normally, you don't need to really worry about the units for these different parameters used in the ABCD model matrix, but they have different notations. If you move to the medium-sized transmission cable, you can see why we have this unit. Just give me 2 minutes, okay? Yeah. So everyone, so now finish it. Regarding the answer of Papi, do you think this answer is right? Numerically, right, but not complete, because for the line-to-line voltage, you need to indicate the angle is a vector. So I think this answer is incomplete. But my question is, based on this solution given here, we have already got at the sending end, the phase voltage is given like this. So this, you can see at the rightmost of the equation, we got L to N. This means line to neutral. This is phase voltage at the sending end, right? And we got the phase voltage at the sending end to be 20.47 with 2 point something degrees. What will be the vector of the line-to-line voltage at the sending end? Okay, I know the magnitude. So square root 3 multiple 20.47. So no problem, that's okay. What will be the angle? I'm asking you this question. Should I add 30 degrees or minus 30 degrees? For Y connection pattern, the line-to-line, for balance system, of course, the line-to-line voltage is always longer. So square root 3 times the magnitude and leading. So please add 30 degrees on the angle 2.732. Is that okay? Everyone, all good? Again, for this question here, so if you want to write down a full vector of the sending end line-to-line voltage, that should be sending end line-to-line voltage is equal to longer and leading. Square root 3 means longer, and 30 degrees means leading, multiple the corresponding phase voltage. Of course, the sending end phase voltage. But the sending end phase voltage has been derived at the previous step. So now we just need to use square root 3 multiple, what that, 20.47 as a new magnitude. And for the angle, it should be 30 degrees plus, so whatever, 2.7 degrees to get a result. Is this okay? Yeah, go ahead, please. If your system is balanced and if the connection pattern is a Y pattern, then yes. So again, for the Y connected pattern, balanced system, the line-to-line voltage is always longer and leading. And the angle must be 30 degrees. And the size, the scalar, might be square root 3. But if you got delta 1, it's another story. So we mentioned this one in our lecture. Please refer to our lecture slides. Okay. Okay, this is about the PAPI, so it should be pretty simple. Any questions before we move on to the next part? Go ahead, please. Hold on, slow down here. ABCD model. So we want to solve the VS, right, using this formula. Do you mean that? You don't have to. So actually, shortly in the question number 2, you can see we can use the line-to-line voltage directly.
But then the second term will never change. Because
yeah, that's true. Because you got a Y pattern, so IR will not change. But the angle and the magnitude of the VR will change. That's okay. So the result, you can double check that after this session. So the result, if you are working on the line-to-line voltage on both of the receiving side and the sending side, it should be compatible with the result derived from the PAPI solution. Okay? Yeah. Sorry for my safe writing, but okay.
Didn't you define VR line-to-line 0 degrees?
VR line-to-line. Okay. So for this case, so because you have 2 different options. The first is using receive side receiving side VR phase voltage. The other one is VR line to line. But no matter which one you are using, we are using it as reference. Right? So if you decide to use the line to line voltage at the receiving side, this VR line to line is reference. So what do you mean add 30 degrees? You mean line to line voltage, right? So okay, here your question is in the ABC model here, if we are using the receiving side line to line voltage, so this will be 0 degrees, no problem, right? You don't have to, because if you are using line to line voltage here, this VS will be the line to line voltage as well. Yes, so the 30 degrees will be applied only when you when you convert the phase voltage to line voltage. But if you are using line to line voltage on the right hand side for VR, this VS has already been the line to line voltage at the sending end. You don't need to consider that 30 degrees anymore. Oh, good. So everyone okay? Okay, let's go back to our question. We don't have too much time, so I don't want to do the question number part C of question number 1 because exact same procedures. The only difference is we are getting a power factor 0.9 leading. So the only difference is leading and lagging. Oops. That's right, yes. So is that okay if I skip the part C? The only difference is angle. So because for part B, our angle is negative 25 degrees, but if you got leading, the angle will be positive 25 degrees. And by substituting this value into the ABCD model, you will be able to solve the VS. Value will be different, the angle will be different, but the procedures, our approach will be same. Any other questions? Okay.
Can you back to the apparent power equation?
Apparent power thing.
Yeah.
My
question is.
hold on. 1 second. You mean this? You mean this equation?
Yeah. Is that a vector or just a single value?
You mean for this case, right? So actually, we said for this formula, we are actually calculating apparent power. Apparent power S is actually the magnitude of the vector complete power. So this is a value. On the right hand side, you can see no matter equation 1 or equation 2 you are using, number 3 or number square root of 3 are all numbers. This V5 or VLL, they are all magnitude of the phase voltage or the line to line voltage. And this current, 1 second. Okay, this current I are actually magnitude of the vector current. So in other words, on the right hand side, they are all values, not the vectors. So if you use these values to calculate the apparent power, this apparent power is just the value. In other words, only the magnitude of the vector. So we do not have any angle information in the apparent power. Hello? Make sense?
Yeah.
So in other words, after you use this way to calculate the current I here, this I is a single value. But as I mentioned, the I must have must be the vector in the ABCD model. So we must solve the angle of this current I. So it's why we have to go through this calculation to determine what is the angle of this current I.
We just ignore the angle.
No, you can't ignore the angle. You need the angle. So in this power calculation, the angle information was not included. So from this equation, you can derive the magnitude of the current I only. But in the ABCD model, this current must be a vector having both of the magnitude and the angle. Because from this equation here, we can get only magnitude. So you have to keep calculating what is the angle of the current. Like this. Is that okay? Okay, good. Okay, everyone, let's move on to the question number 2. Let's move very quick, okay? In the question number 2, 200 kilometers. Okay, for this transmission line, what model we should use? 200 kilometers, question number 2. So what transmission line models we should use? Yeah, because it's greater than 140 kilometers, right? So we're supposed to use medium-sized transmission cable. Of course, still ABCD two-port network model, but we need to be careful with the ABCD these parameters. Okay, so 230 kilovolts, 60 hertz, three-phase line has a positive sequence, so same conditions. Okay, and impedance is Z equal to 0.08 plus J 0.48 ohms per kilometer, and a positive sequence shunt admittance. Okay, this is new content for this case. Be very careful with shunt admittance. Okay, this unit is Siemens per kilometer. At full load, the line delivers 250 megawatts. So what power is this? The unit is megawatts. Real power, yes, because only for real power, active power, we have the watts as unit. Okay, so in other words, the P at the receiving side is 250 megawatts. Okay, and the power factor 0.99 power factor lagging, and the voltage is 220 kilovolts. So using the nominal pi circuit, calculate ABCD parameter. So what's time now? So guys, we have to move quickly because we don't have enough time. Okay, so let's just move very quick. So I think part A of the question should be pretty straightforward. You may refer to our lecture slides to know the formula for the ABCD for parameters. And for this medium-size transmission cable, we are using the ABCD to be the parameter matrix. And I don't want to copy the formulas. We can refer to this one. First of all, along the diagonal direction, the A elements and the D elements must be the same for this system. So A and D are equal. The formula is 1 plus half of the Y by Z. The Y is total admittance of the transmission cable. The Z is total impedance. So we need to use the total transmission distance, 250, multiple the lower Z for the Z. And for this case, you have to use, it's not 250, it's 200 only. 200, right? And this is 200 by lower Y. Again, for saving the time in the class, I am skipping that. Just 1 second. Okay. And then for the calculation, that should be pretty simple. So half is given here, and this is the unit length admittance, and multiple the transmission distance 200. Why we have 90 degrees here? Okay, thank you very much. Good work. Okay, don't forget this should not be a number. So you should include this J because it's part of the comp number. Okay, this is corresponding to the J. Keep going. 200 kilometers multiple the unit size impedance. So after this calculation, so you will be able to get the A and D, these two parameters. And keep going to C. C equal to this pretty long one. So Y multiple 1 plus quarter of the Y by Z. Again, the same issue. Just do calculation by yourself. Okay. So result is given here. Finally, for the B parameter, this is the easiest one. The B parameter is just equal to the Z. And after all these calculations, so we have determined our ABCD transformation matrix. So the whole thing is done in part A. Should be easy, okay? Okay, to that. For part B of the question, the standing and the voltage and the current. So here in this question, let me have a quick look. So at full load, the line voltage is right. So we are going to determine the standing and the voltage and the current. So we are going to use our ABCD model. So in the part B, so V as I as this vector is equal to same thing, ABCD multiple VR IR. The same thing here. ABCD, these four elements are known, so no problem. So next question is VR and IR. The receiving side voltage, so here we assume, so we want to keep it compatible with the solution. So we are assuming this VR is the phase voltage at receiving end. Okay, so now in our solution, you can see here, VR is converted from the line to line voltage to the phase voltage by dividing the magnitude with square root of 3. Angle is 30 degrees because we are using this AR to be the reference. So that's the easiest step to run same as before. Regarding the IR, the current calculation, okay, you may think this formula is really complicated. The reason is in this one single formula, we are calculating both of the magnitude and the angle. But for me, and also for yourself, I want you to slow down to divide this into 2 steps. First one, calculate what is the magnitude. In this question, we have been given the real power. So at the receiving side, we got real power, which is equal to, guys, can you remember the formula? 3 multiple receiving side phase voltage multiple the current of the receiving side. So it doesn't matter phase or line current, and multiple what? Real power is the projection of the coupling power along the real axis. It's always multiple cosine theta, like this. Okay, and then from the first part, you have got the phase voltage. Real power is given. Number 3 is constant. You want to determine what is the phase current. So your question is only the cosine theta. But we have been given the condition that this receiving side is 0.99 power factor lagging current lags voltage. So using the same way, you can determine the angle of the current compared with the angle of the reference VR voltage. It should be negative as well because it's lagging. I skip this one, okay? And then by putting that angle into this one, anyway, I'd like to slow down. What is this theta? This theta is actually a theta in the power triangle. This theta is equal to theta V minus theta I. But theta V is a voltage, the angle for the voltage, which is a reference. So theta V equal to 0 in this case. And you can work out the theta I. Then 0 minus theta I, you got this theta. Based on this theta, you should be able to determine what's IR. That is the magnitude of the current. What is the direction of this current? Because of that 0.99 power factor lagging, you should be able to derive the angle, which is negative. And then by combining the magnitude and the angle information together, you got the IR vector. So again, I am skipping this result. So the result should be given like this. Double check your work. Now we have noted VR and IR, these two vectors, and then put that into the right-hand side of the equation. Using A and B, these 2 parameters in the ABCD model matrix, you should be able to solve the VS. That VS should be the sending end phase voltage. And again, you got to balance the system. So you may convert that to the line-to-line voltage, then finish. Is that okay, everyone? Okay. Finally, be quick anyway. Part C, what is the percentage voltage regulation? So in other words, for this part, we are going to determine the VR, voltage regulation. Can you recall the formula for the voltage regulation? Actually, voltage regulation equal to what that? V watt minus V watt. No load, be careful, minus full load divided by full load, just that, okay? Actually, the full load one is simple. The only question left here is, what is no load voltage? So here we need to understand what is no load. No load means at the receiving side, no load is added. If there's no load is added to this circuit, so the single phase circuit looks like this. Transmission line. VS here, because this is medium size one, so we have the admittance. So 2 capacitors, 1 on each side. So one is getting here, and the other one is getting here. And our load should be added to this side. This is receiving side. This is sending side. We have the VR here. We have the IR. We have the IS. Sorry for rushing. We don't have time. Okay. But here we are saying we do not have the load. The no load voltage means the voltage across the 2 open terminals without load. If you do not have load here, these 2 terminals at the receiving side are open. If they are open, so no current can go through that. That means IR equal to 0. By using this information in our ABCD model, we can simplify the work like this. So we are focusing on the VS and IS thing, right? And the ABCD, these 4 elements, remains unchanged. But at the rightmost, first of all, no current at the receiving side. The current is 0. Correspondingly, the voltage at the receiving side is no load voltage. And the question is asking us to determine what is the no load voltage. So we want to determine this term here. So let's just focus on this Vs, AB, and this column here. So Vs equal to A multiple the no load voltage plus B multiple the 0. B by 0 is just gone, is 0. So the remaining thing is Vs, the sending end voltage, is equal to the A element multiple the no load voltage. So the no load voltage equal to the sending end phase voltage divided by the A. Of course, again, I want to remind everyone, this Vs here should be what? Should be a vector or should be a value? Vector or value? Should be vector. Should be vector. But when you calculate the voltage regulation in this formula here, all the terms are only values, no angles. So theoretically, by using the ABCD model, this Vs should be a vector, but we focus on the magnitude of it only. You can save some work because angle, yes, okay, you can just involve the angle, but it's not necessary for the calculation of the voltage regulator or regulation. Okay, so actually in our work here, given the solution, you can find, and we have only the values left. Okay, this is a tricky thing because by using the ABCD model, you should derive the vector no load voltage, but you are using only the magnitude to finish the calculation. Okay, guys, sorry for delay, and sorry to say we can't finish the remaining questions. Please try out the question 3 by yourself. If you still have a problem, we can discuss that in next week by Professor Tyrone. And I think the question 1 and question 2 should be fine. So any other questions? Thank you everyone for attending this class. See you on Wednesday. Okay, online students, you have questions here. This phase, second. So phase, second would be better. What do you mean? Okay, yeah, I know what you mean, Liang Yu. You can use the phase voltage, yes. Is the appended power a vector as well? No, appended power is a value. Middle, one question. But anyway, okay, I think we have solved the question. Thank you for one question. How you determine 250 millivolts? What do you mean 250 mega? You mean question 2, right? Okay, this 250 megawatts, right? Because its unit is watts. So only the real power has a unit watts. And for appended power and complete power, it will be VA. And for the reactive power, its unit will be VAR. But so you know the unit, so you know this might be real power. Is that okay? Okay, good. Thank you guys, and we have to finish now, and see you guys around. Bye for now.
There it is. This is line-to-line voltage. Should be. Yeah, 33 kilowatts line-to-line. Yep. The solutions. The solutions converted it to phase voltage. Yep. But here, you define line-to-line voltage 0 degrees.
Yep. This is our assumption.
Does it matter?
Doesn't matter.
Doesn't matter
because actually all the phase angles of other current voltage stuff are referring to
Okay, so here you use this as a reference, but the solutions use the phase voltage reference. They're two different references.
It doesn't matter. So when I mark the works, I will just say which one you are selecting to the reference.
So in this case, if you use this as reference, at the end, when I get the answer, I put in 33, 0 degrees, and then mark 0 degrees, and then I get VS finished. That's it.
Your VS should be referred to your assumption. Yes, that's it.
So the VS line to line will be like
VS line to line.
Will be like
refer to that one, something like that. I can't remember numbers.
So when you were talking about adding 30 degrees, that you only add 30 degrees if you
are converting from the phase voltage to line voltage.
If your phase voltage, if your reference voltage is the phase voltage, then you only add.
Yes.
if your reference voltage is the line to line,
And you want to convert this line to line voltage back to the phase voltage, then you have to take 30 degrees.
yes. Wait, I never converted them.
And you don't have to. You don't have to. I mean, if you want to do
Yeah,
that.
but we didn't even here. We even used the square root.
Yes, that's true.
Yeah, this is not vectors.
Yes,
This is
you have to change the whole set of equations. That does make sense.
I don't need to convert.
Does class make sense? Not
Easy.
quite.
No, it's just the 30 plus 30.
Yeah.
But it's like, no, I shouldn't add. Maybe I should add another.
If you are in line to line, you don't have to. Yeah, go ahead. Yeah.
直接说中文，直接说中文。是能听懂吗？
Okay, line to line voltage. So let's do how this. Because we are assuming all the connections are in Y pattern, so if you have this one, so that's the generator here, and we have some transmission cables like this. So phase A, yeah, phase B, phase C, whatever, and sometimes you have neutral here, and the phase voltage, the voltage, of course, at the transmission line is neutral, because transmission line is neutral is just, of course, it is rising phase, because it's a phase voltage. VA, VB, this is stuff, maybe this is center here. And the line to line voltage means the voltage, of course, two transmission lines. Two transmission lines. So not the neutral line. So line to line voltage is here. Because two lines are not neutral. So this is called line to line voltage. If your system is balanced, so the line to line voltage is stronger than the phase voltage. Again, only for balanced Y pattern, right? The line to line voltage magnitude is square root 3 times stronger than the phase voltage. And also, this magnitude, yeah, and that leading thing is the angle of the line to line voltage is 30 degrees leading than the phase. You see the VP is in here, so it's 30 degrees leading. Yeah, okay. Actually, in our lecture meeting, week 2, we will mention this quickly. Okay.我没发邮件，我发的是 announcement。不过他应该也是送到你的那个线上去。我得找到一个课，好吧？有问题再问吧，好吗？好嘞。
我们国内学是那个一个线，那个一次网和二次网接口来调那个。
后面有学的，但是生产程序这它也是很基础的。
是，但是你这先手头你基础概念给忘了。
没关系吧，这有问题再问吧，好吧？好的，那今天上课听得懂吗？就是有点计算，有一点点不知道，学多还是？
但是那个向量那个我得好好看一下。
向量指些角度，这个得最重要是找。
对。
其实说实话，肤值倒不是很重要，也不是不重要，就是没那么难，向角比较对。
对，那个我就不会算，那个一除我就感觉就很难。
那问题就是我们改成线上的课，就我们有课程多改成线上课之后，你要考试的话，我们这个是吧还要
就参加online考试。
哦，
这个还没最后，人家考试test 是在这学期后边了。
哦，
我没给你看。